Hello, Professor Rashidi. My name is Deni Vojnikovic, and for my Project 3 presentation, I'm just going over a couple interesting principles I found learning with you in ME 3210. So for my first topic, I went with non-destructive testing techniques, and I chose this because I find the contrast between non-destructive and destructive techniques very interesting. How there is this kind of trade-off between if you destroy a product, if you're willing to break it down, you can get a lot more information out of it. But sometimes there are circumstances where you can't just break down a thing and you need to find some way to still analyze it without destroying it. Getting into a summary, the summary of non-destructive testing techniques is very simple and kind of on the tin. It's any kind of testing technique which doesn't damage the subject, that whatever you are measuring or analyzing is still immediately usable as soon as you're done with the testing. And some of the primary testing ones that I kind of found of note was ultrasonic testing, dye penetrant testing, and magnetic particle testing. Now I chose all these because they all have a very similar case use and kind of purpose of existing, with a few small differences that kind of distinguish them and give you reasons to do different tests. Ultrasonic, as seen on the far left, the main principle is that you send a ultrasonic vibration through the material, and theoretically there is a signal you would receive if the container had no cracks. But then if there was a crack in the way of the vibrator and the end of the piece, you would have some slightly different signal because the ultrasonic vibration doesn't travel nearly as far. Then getting to dye penetrant testing, the main principle of that is that you have some kind of workpiece that theoretically has cracks. If you clear out any of the cracks so that they're actually empty and can be filled, apply a dye to them, clean off the surface dye of any excess that was left, you can have a very clear indication of where cracks are. Because it can be really difficult when the cracks are super small and thin and basically the same exact color as the material. Having some kind of dye to penetrate and fall into the cracks lets them become a lot more visible. And this is primarily used on non-ferrous materials, whereas magnetic particle testing is able to be used on ferrous materials because ferrous materials are magnetic. And it is essentially that when you introduce a magnet to the system with a crack in between, that crack can cause some leakage of the flux in the magnetic field, which can then be recorded by some kind of testing material to prove that a crack is present. The primary capability of non-destructive testing is that it preserves the subject. That whenever you're doing the testing, you don't have to damage it. Whatever it is, you can immediately put it back into its use case, and it's perfectly fine. And then that ability to preserve the subject naturally kind of branches out into a bunch of other benefits. It reduces costs because you don't have to destroy any products to do the testing. So whatever you use it on is still good. You don't need to buy a new one. And also it can be used on things that you can't replace or remove from its environment very easily. If you have some sort of giant pillar that's being used to support something in a building, you can't take that out. You'll destroy the entire building. So having the ability to do non-destructive tests is incredibly useful because it doesn't remove it. And on top of that, non-destructive tests can be very versatile in that humans have been figuring out a ton of different ways to do non-destructive testing that are useful for specific materials. That's you have magnetic particle testing if you have a ferrous material. If it's non-ferrous, you can use dye penetrants. But in terms of limitation, there is a problem of scope with non-destructive testing, that there are things that you cannot acquire about a system without destroying it. You cannot get the yield strength or the ultimate strength of an item through non-destructive testing. The only way to make something yield is to put enough force to permanently deform it. The only way to break something is to exceed its ultimate strength. So there are a few aspects of things that non-destructive testing just can't cover. In addition, it's always dependent on the nature of the material. You can't do magnetic particle testing on something that isn't ferrous. It's just not designed for that. And in addition, the testing equipment itself can be expensive or particularly specialized if you're working with really specific materials, and it requires some kind of experienced technician who understands how to actually use this equipment and use it appropriately and understand what to use when. Going from non-destructive testing, I also chose to talk about destructive testing in the same vein. I find it really interesting to look at the comparisons between what non-destructive tests can give you and what destructive tests can give you. Now, destructive testing, much like non-destructive testing, vary on the tin, is any kind of testing in which the subject would be damaged or become dysfunctional as a result of the testing. And arguably like the perfect example of it that is very common is crash tests in cars, as well as stress and strain tests to test the material properties of things, as well as kind of an interesting note, destruction doesn't always necessarily have to be a physical thing. There is such a thing as destructive software testing. And just to briefly explain them, of course, crash testing, you take a car and you run it into a surface to see how the car deflects and brakes, as well as like what is the physical response of a human in that system. With things like stress testing, you're taking a small slit of material and constantly applying either a compressive or a tensile force to find various physical attributes of the system like yield strength, ultimate strength, buckling load, etc. And with destructive software testing, the intention is to take some form of software and be as aggressive and sort of dysfunctional with it as possible to see where the software can fail. That it's like, oh, if I put in a ridiculous number, do I get an overflow error that like crashes the system? It's the like fundamental idea of finding where a software can crash by just using it in a very extreme context. Getting into capabilities and limitations, the big capability of destructive testing is there's a lot of information you can get out of something by destroying it. And by destroying things, you can ensure the safety of those things. By showing like, hey, this piece of metal breaks in half when you apply 370 megapascals of pressure to it. Now we can understand the actual limits of these things and use those and account for those in future designs. As well, it's versatile. Humans have been destroying things literally all of our history. There are a ton of different ways to destroy things and get information out of that. As well, limitations-wise, it of course eliminates the subject. It breaks things, which can be incredibly expensive if you're talking about expensive things, as well as it can be very resource intensive because now you have a thing that you can't like use again. You just need to keep putting in more material as you keep testing it. Getting into the third subject, I chose forging and its various types. I just find it interesting in that going through the lectures, it seemed like there's so many different ways to just pour metal into something and make it into something useful. Forging is, of course, the process of shaping a metal into a particular shape through primarily hammering, pressing, or rolling. So you're taking some kind of object of metal and through a process putting it into the shape that you want. And just as some types that I cover here, I have impression die forging, closed die forging, and hot die forging. Keeping things brief while we run out of time, just as some examples of forging and its capabilities, impression die forging and precision forging, both very similar in that you just take an insert, squish it down, and it makes a shape. The difference being that precision forging, you take a very specific insert so you don't develop any kind of flash. And then with things like hot die forging, where instead you heat up the raw material beforehand so that it's a lot more elastic. Pretty much just forging has a ton of capabilities. There's a ton of different ways to use it. At least in terms of limitations, it's purely used with metals. However, there are plenty of processes for all non-metals, so it's pretty much a non-issue. Getting to the fourth topic, I chose deep drawing because I find it to be a really interesting way to make very specific shapes. Getting into what deep drawing actually is, it's a process in which a sheet of metal is essentially drawn or like pulled down and deformed by the mechanical action of a punch. With the essentially the concept being like you have a sheet, you have a little radial thing. When you push it down into it, you deform it into some kind of circular object. Which is used in a ton of different things, primarily beverage cans, kitchen appliances, containers, anything that is relatively radial and can be made from relatively thin sheets of metal. Going into capabilities and limitations, deep drawing is incredibly useful because it's super high speed and efficient, and it can be made to be very precise. However, in terms of limitations, like frankly most like factory production systems, it has a really high initial setup cost. These machines are incredibly expensive. They can also have to be incredibly specialized. You need to like know what type of shape you're deep drawing into. There isn't any like generic deep drawing machine. In order to deep draw, you need some very specific molding. As well, deep drawing can be less effective in low quantities because it is a process, because it is so expensive, you need to justify it by producing a lot. Getting to my last subject, I chose centerless grinding because frankly, I find the setup of centerless grinding kind of really interesting. I don't think I've really seen a shape like this before, and I wanted to do a little bit more research to understand how centerless grinding actually works. In terms of how centerless grinding works, the main principle is to use abrasive cutting to remove material from a workpiece. How it does that is that you just put the piece of metal through it. You have one wheel that moves purely to keep the system rotating, and then another one which slowly comes in and applies pressure to actually start causing abrasions on the cylinder, slowly chipping it away. It differs from centered grinding operations in that there isn't a spindle or any kind of fixture that you use to hold the workpiece in a specific location. Instead, you're relying on this second moving wheel to support it while you grind it. And centerless grinding is usually preferred in operations where you need to do your grinding in a very quick amount of time, because you don't have to do any kind of setup of like making sure it's properly attached to this fixture. You just put it through the system. In terms of capabilities and limitations, the main thing with centerless grinding is that it's really good with high production rates, specifically because it can be fed automatically. You can just continue to push a cylinder into the wheel and it'll just continue to grind it. In addition, the machines themselves have very long lifespans because they're very large, powerful machines. There's not a lot of chance that a workpiece is going to damage it in any way. In terms of limitations, they are, of course, extremely expensive and take a lot of time to set up, as most large machining systems are. Also of note, it's very limited to the fact that it only works in one axis. You can push a cylinder into it, and that's kind of it. And they can only work on the surface of the cylinder. As well, there are some material challenges in that by shaving off from a workpiece, you can get a bunch of shavings and scrapes and little bits of metal dust that then need to be cleaned or moved out in some way. It can be a problem if those shavings get back into the system and start grinding into the workpiece as well. Finally, in terms of references, most of these are just locations where I got various images, particularly the notebook I used for a couple definitions, but primarily for the images. As well, I used Wikipedia as just a nice starting place to get some understanding of the core principles. And the other 4 sites are just locations where I got various images. Thank you so much for your time and have a wonderful day. Sorry for going over.